Well, last time we took a look at the Dirichlet function, which, let's remind ourselves what it is. The function is either equal to 0 or 1 at every single real number. It's equal to 1 if x is a rational number, so f of 0 would be 1, f of 2 would be 1, f of any rational number would be 1, and for the irrational numbers, it's equal to 0. So this is kind of how I graph it. Just put a bunch of dots here and a bunch of dots here. So for each one of these, that's where x is equal to a rational number. It has a height of 1. And the irrationals has a height of 0. Well, the interesting thing about this function is that we've already seen this. For any x naught that you pick, any real number, the limit as x goes to that number does not exist. And we proved that last time. We're going to prove it in just a slightly different way this time. But effectively what we did was, in the proof, we said, well, suppose the limit exists. That means that somewhere, the capital L is the limit, somewhere that exists. I just drew it here. I could put it up here or down here. It doesn't matter. If the limit existed, then for any epsilon greater than 0, I'll draw an epsilon. So let's say that this is L plus epsilon, and say this is L minus epsilon. So my epsilon is a number that's that big. So it could be like a fifth or a sixth or something like that. If the limit exists, and I'll draw x naught, say right here. I don't know whether x naught is a rational number or an irrational number. I know it's one of them. Well, at no point when I'm getting close to x naught are all of the values of the function in this little region, this little L plus epsilon, L minus epsilon region. They would all have to be in there in order for the limit to exist. And I think we used a little arithmetic fact last time where every real number is distanced at least 1/2 away from 1 or away from 0. So essentially, it doesn't matter what delta I choose. This would be x naught plus delta. This would be x naught minus delta. It could never be the case that all of the numbers in here, all of the x's in here would have an f of x that falls within this L plus or minus epsilon. That's kind of what we did in the proof. Well, we're going to prove it in many ways. It'll look different. In many ways, it'll look the same. We're going to use sequences. We're going to use theorem 2.1, and let's review what that said. The limit of a function, dx, for example, at some number x0, x naught, if that limit exists, that means that for every sequence that converges to x0, every sequence xn, f of xn is going to converge to the limit of that sequence. So this is our second method to show that the limit at x0 or x naught does not exist. And x naught is just arbitrarily chosen, any x naught. We're going to use sequences and theorem 2.1. So specifically what we're going to do is find a sequence xn that converges to x naught, but f of xn, that sequence, does not converge. And that would prove that the limit doesn't exist. All right, well, I'm kind of going to do it just one direction. I'm going to assume that x naught is a rational number. So suppose x naught is a rational number. It's an element of Q, the rationals. I'm going to put a little comment in here that says if x naught is not in the rationals, which means it's in the irrationals, then the proof is similar. So I'm going to come up with a sequence, and let's just write it down. X naught plus 1 over n. That sequence converges to x naught, obviously, right? We're adding a number to it that decreases to 0 as n goes to infinity. So this converges to x naught. And what do we know about, in this case, what do we know about f of xn? Remember, we're assuming that x naught's a rational number. So what is f of x naught plus 1 over n? We're just adding a fraction to it, another rational number. So it remains rational. The whole sequence is rational numbers. So rational numbers, oh, sorry, this is not f of x, it's capital D of x, n. And so it's, let's see, so should this be? I'm so used to writing f of x, but we're using capital D of x now. Let me know if I missed any others. Okay, well, what is this sequence? Well, it's this sequence. And that converges to 1. That's not the sequence that's not our final sequence, but that's one to look at. Okay, any sequence of rational numbers, is going to convert f of x of that sequence, or d of x of that sequence would converge to 1. Any questions on that so far? Now I'm going to create a second sequence. It looks similar. Make sure you're convinced that, oops, put the 2 in the wrong spot. This is going to be x naught plus radical 2 over n. So what type of a sequence is that? Right here. X naught is a rational number. So what do you get when you add a rational to an irrational? You get an irrational number. So now I have a sequence of irrational numbers that converges to x naught. And we know that means that d of xn is equal to the sequence 0, 0, 0. That converges to 0. And this is actually one way I could almost stop the proof right here. But I didn't quite do what I said I was going to do. I'm going to come up with one sequence that does not converge. I came up with 2 sequences here that both converge to x naught, and f of dxn converges in both cases. So how could I come up with one sequence, you think, that does not converge as x goes to xn? I mean, we could, as I mentioned, we can stop the proof right here. I found 2 sequences. Remember what theorem 2.1 says? I kind of said it already. If you find 2 sequences converging to x naught that converge to an L1 and an L2, two different numbers, that means that the limit of that function doesn't exist there. So we're done. And maybe I will stop here, but I'll tell you what I was thinking. And tell me if this makes sense to you. What I was going to do is take one element, the first element I'll take from this sequence. And the second element I'll take from this sequence. And the third element I'll take from this sequence. And the fourth element I'll take from this sequence. And if I write that up, what does the sequence look like? Which one did I start with? This one? It would go 1, 0, 1, 0, 1, 0, forever. So we have an oscillating sequence, so obviously it doesn't converge. And that's enough right there to show that the limit doesn't exist. We found a sequence that converges to x naught, but this d of that sequence is not convergent. So by theorem 2.1, the limit does not exist at x naught. So I think I'll stop it this way. We found 2 sequences converging to x naught, and d of those sequences converge to 2 different numbers.